Welcome to Real Physics. This is about the Machian Gravity Meeting recently held in Bonn with Dennis Braun, Jonathan Fay, Jan Preuss and myself. The talks and discussions are a little bit more technical than usual, thus if you're interested in the details I encourage you to look up my variable speed of light playlist or the papers linked in this video. Enjoy watching. Okay, welcome to the talk of Dennis Braun, who is a physicist from Bonn, and he is working in the Andrew Wilson style of years working, calculating, and then coming up with very interesting results. And I'm curious to hear about Jürgen Treder and his findings about Mach's principle and the possible relation to Sciama. Thank you, Dennis.
Yes, thank you. As said, I'm going to talk about the theory of Hans-Jürgen Treder, which he developed in the 1970s, and which I think is really the, so to say, correction of Newtonian theory, and which realizes Mach's principle and the idea of inertia coming from gravity. Yes, and one observation which one has to make is that the problem really is the Newtonian kinetic energy, which is something like the sum over all the masses, and then we have the mass of the ith particle over 2 times the velocity of it squared. And this object contains absolute quantities, which is this velocity, and also only a single mass mi occurs here. If one wants to make this Machian, then it has to only depend on relative quantities. This is also an observation which has been made by Lyndon Bell. He published a paper about this in 1995, where he tried to correct this mistake. And if you do this, you end up with an expression which really has to have this form, mi times mj over, he keeps the factor of 2, and then vij squared, and this vij is the relative velocity between the particle I and the particle j. And the correction which was made from here to here is, so to say, to implement Mach's principle. That this expression does depend only on the relative velocities and on the products of the masses. And in a second step, one can now notice that this already looks really close to the gravitational potential. It depends on both the masses. And if one now goes to the idea that inertia really is a gravitational phenomenon, then one should, here it must say, of course, the sum runs over the particle I and j of the pairs of particles. And here too. Then one makes this first part proportional to the gravitational potential. And for dimensional reasons, one has to introduce some kind of velocity in the last term. And it is convenient to choose the speed of light because it has the dimension of a velocity, and one does not want to introduce another arbitrary parameter, and so one chooses the speed of light. And then the kinetic energy essentially has this form, and it implements Mach's principle. It's Machian, and the idea that that inertia really is of gravitational origin. And with this, one gets for a Lagrange function of the universe something like the sum over j, kinetic energy minus potential energy, and this is something like 1 plus beta ij squared. And here I've forgotten the gravitational constant, it should appear there. And this is the gravitational potential. So in the first term here is the negative of the gravitational potential, and this is the kinetic energy.
Can I just ask to clarify, where did you get the divided by R?
Yes, this was the reasoning that inertia should be of gravitational origin. So this is the implementation of this idea that inertia is of gravitational origin.
And you have just the factor, you just divide by the distance?
Yes, this is to make this proportional to the gravitational potential.
Okay.
That the inertial term is proportional to the gravitational potential. So from here to here is Mach's principle, and from here to here it is the idea that inertia is of gravitational origin. Yeah, and then you arrive at the Lagrange function which Treder got. It is the Lagrange function of his theory. And yeah, now one can make a very interesting observation, that because the gravitational constant appears both in the kinetic and the potential energy, it is just a scaling factor. And the Lagrange function remains invariant under rescaling, so this is of no importance. And the gravitational constant really drops out, and we can just write this as. Yeah, and one sees that one does not have to introduce any gravitational constant a priori, but one can formulate classical mechanics without introducing a gravitational constant. And from this equation, one can actually derive an expression which takes the place of the gravitational constant later. We will see that in a moment. Yes, this Lagrange function describes the dynamics of the universe. Of course, in a non-relativistic, this is a non-relativistic theory, and yes, a relativistic extension of this remains to be found. But I think it is first one has to find a non-relativistic theory, which implements this both ideas, Mach's principle and inertia being of gravitational origin, and then one can try to think about a relativistic version of it. Yes. Now we can take a look at this Lagrange function. If one multiplies this term out, it is something like beta I squared, beta j squared, minus 2 times the scalar product of beta I and beta j. And if one rewrites this, then one gets the sum over.
Just before we canceling, I'm a little bit slow. From the first line to the second line, there's actually a little change in dimension because you get an extra mass in the on top. You have just one mass in the first line, and you have a product of masses in the second line. So is this to be divided by the
yes.
sum of overall masses?
Yes, here you have to put in.
Or you can outside the.
And this is the form that. Yes, this is the form that Lindenbell and Katz got, and yes, that you get an extra m, and this m is something like the total mass of the universe. So it is the sum over all masses, mi.
Okay, and this one over n would just continue to the other lines.
Yes, here it is really replaced by, here the dimensions are correct.
Okay, yes. So
here it is replaced by g over r times c squared.
Okay, that's fine.
And so this is the dimension of an energy, and this is dimensionless, and so you get a dimension of energy.
So let's just take a picture here, and this will be included.
May I also ask, before you wipe it away, is this already invariant under rotations?
No.
Not yet.
No, it is not yet invariant under rotations. This is actually the form of the Lagrange function which Treder used for his theory, and one of the shortcomings is that it is not invariant under rotations. But I corrected this, and I will later write a form where it is invariant under rotations.
Okay, perfect.
And you also have to make it invariant under rotation so it can correctly account for the Newtonian bucket experiment. Okay, now we have the Lagrange function of the universe. We have dropped the gravitational constant, so we see that we do not have to postulate it a priori, but we can write classical mechanics without a gravitational constant. With this Lagrangian, it describes the whole universe. The sum runs over all pairs of particles in the universe. And yes, the first, one interesting thing to notice is then if we calculate the momentum of a particle, it is something like this. And we can write this as ik over c squared times vk minus 2mi over c times a. And here I've introduced the usual definitions of the gravitational potential and the vector potential. There's something like vector potential. So these are the usual definitions of those two. They are the same as in linearized gravity. And one can see that this here is the inertial mass of a particle. This is something like the inertial mass. I will denote it as with a star. And it is proportional to the gravitational potential of the universe. And this means that if the gravitational potential is zero, if there is no gravity, then a particle would have no inertia. If we sum up all the contributions of all particles, pk, this is something like the total momentum of the universe, then because this expression is antisymmetric in I and j, this is zero. So the total momentum of the universe is zero in Treder's theory. And yes, this follows from the antisymmetry of this expression here. And the inertial mass of a particle is given by 2mk phi k over c squared. And this mk here plays the role of the gravitational mass. So we have discovered a relation between the inertial mass and the gravitational mass. And we will see in a second that this yields an explanation for the for the weak equivalence principle, for the universality of free fall. So one does not have to postulate this either, but one gets it out of the theory. Okay, for the one particle Lagrange function, yes, one can calculate from this the Lagrange function of a single particle, and this is something like yes, this is what one gets for the one particle Lagrange function out of this. And one can look at the first three terms here. They are just equivalent to the Lagrangian in an electromagnetic field with a factor of 2 in the magnetic field, and the inertial mass given by this expression. And this means that Treder's theory gives rise to Gravo-electromagnetism. And this is actually what was postulated by Sciama. And we will see that one gets the mechanism, how inertia is explained, that Sciama proposed is the same which comes out of Treder's theory. Yes, and we can, from this, of course, derive the equations of motion. And by applying the Euler-Lagrange equations, and one gets something like the magnetic field, and the electric field is given by, I don't have space for the magnetic field now down here. This is very similar to what one gets from electromagnetism. This here is just the gradient of the potential, just with the correction which arises from the velocity dependence here. And this is the gravomagnetic induction term, just with a factor of 2 here. And the magnetic field, yeah, I will write down after I clean the board. Just one comment to this equation here. It agrees with the Lorentz force equation, just with the difference that it depends on the relative velocities instead of the absolute ones. And the inertial mass is again given by this expression. And this equation here is valid in arbitrary accelerated frames. Not rotationally accelerated, because this is not rotationally invariant, but under arbitrary linear accelerations. And that connects to your talk, because you earlier said that really you have, you must not have laws which are just valid in a preferred set of reference frames, but they should be valid in arbitrary frames. And this is exactly what this equation is. It is valid in arbitrary accelerated frames.
Right. And it's so that you have that any transformations that keep the shape of things and like the relations between things constant, the same, should not interfere with the physics. Shouldn't like interfere with. So yeah, well that's how I would phrase it.
Okay.
Any like shape preserving transformations.
Yes.
You're referring to Barbour's concept of shape invariance. It's kind of introduces another kind of symmetry, right?
Exactly. Yeah. And I think that's also something maybe we could mention, that as well as the symmetry on the rotation that Mark talks about, you should also have another symmetry under scale transformations, right? Because if everything doubles in size, just like if the universe is rotating, you don't know if it's meaning. And if the universe doubles in size, everything stays the same because you still measure everything the same.
Yeah, I mean that's kind of the varying scales cosmology I was proposing in the spirit of Dickley, because I mean if everything is growing, you wouldn't notice immediately, but you need other.
So yeah.
I mean, and this it really does not have to do anything with scale invariance, but with invariance under transformations in accelerated frames.
Yeah.
So it does not matter if your frame is accelerated or not.
So
but the laws stay the same.
Generalized like rigid transformations. So any transformations that keep the shape and the size invariant, so they move around them. Yeah.
Okay. Yes, this is also not very surprising. It's very similar to the expression for the magnetic field in electromagnetism. The expression which we just found depend on this parameter beta, so this is something like V over C. And if we take the lowest order of this, then we just have the equation of motion as. So we have something like this. And this is actually Newton's law of gravity. And we can divide by this quantity, and then we get the acceleration as. If we recall that mk was the inertial mass, which was given by this expression, then we see that the masses cancel out, and we remain with c squared over 2 times phi. So we have, and this is something like the gradient of the potential. Yes, and this is just Newton's law of gravity, but with the gravitational constant given by this expression. This is the gravitational constant. So we see that without introducing any gravitational constant, it just comes out as a consequence of the theory. We do not have to postulate it, but we get it out of the equations. And it is given by c squared over 2 times the gravitational potential. This is of course position dependent, and yes. And what we also get is the weak equivalence principle, because we saw that the masses here cancel out, the gravitational masses cancel out, and all bodies fall with the same acceleration in the gravitational field. So we do not have to postulate it either. It is a consequence of the kinetic energy term being proportional to the gravitational potential, because we have explained inertia as of gravitational origin, we get the weak equivalence principle. now to the inertia. Yes, we can write this. We had the equation of motion in this form. This was the equation which we had on the previous board. And if we go into the rest frame of the particle, then this term here is 0. We established that it holds in, one can show that it holds in arbitrary accelerated frames, so we can go in any frame we want. And in the rest frame of the particle, this term is 0. So in the rest frame, we just have Ek minus 2mk equals 0. And this equation expresses that in the rest frame of the particle, the whole gravitational field vanishes. And this is exactly what Sciama had postulated.
Yeah, exactly.
And it comes out also as a consequence of the theory. And yes, but here one does not have to postulate it, but it is a consequence of the theory. It is built into it. And from this, if we go back into the, if we transform out of the rest frame into any other frame, then the particle will move with some velocity in any other frame. The particle will move with some velocity vk, which is perceived there. And if we look at the definition of the electric field, it is something like this first term here, dt. So this first term here is invariant because it depends only on relative quantity, so it has the same form in whichever frame we write it. But the last term here depends on the velocities of all other particles, beta j, in the universe. So if we transform this expression into another frame, this term stays the same. But this here will give us something like, now I need a new board. I will write the expression for the electric field again. So this stays invariant. So if we transform this into another frame, then we get something like, and this is just the gravitational potential. So, and if we plug this into here, then we get that this just transforms like something like this, minus an additional contribution of 2 phi over c squared times dv after dk. So we get out, if we transform into any accelerated frame, we get this additional acceleration term out of the gravomagnetic induction effect. And then we reobtain, if we bring this to the other side again, then we reobtain the equation of motion in this form. So we see that just like in Sciama's theory, the inertia term comes out of the electric field. It comes out of the, it is part of the gravomagnetic induction effect. And yes, comes out when we transform out of the rest frame of the particle into any other frame. Then we get this acceleration term on the left side is actually just a manifestation of the gravomagnetic induction effect. And in the same way, this also implies that the theory yields the inertial forces, because in whichever accelerated frame we go, we get an additional acceleration term, which is proportional to the acceleration of the frame that we transform into. So the Newtonian fictitious forces, they do not have to be postulated anymore when you go into an accelerated frame, but they come out of the theory. The gravomagnetic induction term yields these inertial forces. So this was for linear acceleration. And yes, before we go to rotational acceleration, just one remark concerning the gravitational constant. We saw that the inertial mass is proportional to 2 phi over c squared, and the gravitational constant is just the inverse of this. So we got the gravitational constant in Newton's law because we divided this inertial mass on the other side and got a prefactor of the gravitational acceleration. So one can actually explain why the gravity is such a weak force, because the yes, it is not actually the gravitational law which has the g factor built into it, but the inertial masses which have the inverse of it built into it. And then if you divide by the inertial masses, then you get the gravitational constant. So and here the so we see here doesn't appear any constant. It is just the product of the masses divided by the distances. So we have no gravitational constant in the gravitational force itself, but we have the inertial mass here, and this factor here is just the inverse of the gravitational constant. And if we multiply this over here, then we get, this was the gravitational constant here. So, and one can explain the strength of gravity, because since we have so much masses in the universe, the inertial mass, which is induced by all other masses in the universe, is a very large quantity, because this phi here is proportional to the sum over all the masses. And therefore the inertial mass is very large, and then gravitational accelerations are very small. If there was considerably less matter in the universe, then this phi would be a much smaller quantity, and the inertial mass would be very much smaller, and then the gravitational accelerations would be larger. And this is just expressed by the fact that the g is the inverse of this factor here standing by the inertial mass. So if the inertial mass would be smaller, then the g would of course be larger, and gravitational accelerations would be larger as a consequence too. Questions?
What's that?
Questions?
Well, I'm just wondering whether, like, how close is this stuff to Assis's work, if you've looked into that?
Yes, Assis made one crucial mistake. It is very similar, but he chose a Lagrange function which is...
Because he tries to do an analogy with Weber's law, right?
Yes, exactly. He uses Weber's law, and with Weber's law, this reads something like this. I'm not sure about the constant here, but it is something like Rij point squared over c squared. And this is the rate of change in the distances.
Okay.
But this leads to anisotropic inertial masses. So if you calculate the inertial mass, here this is a scalar.
So that's different from the relative velocities?
Yes.
How come there's a difference there?
Rij is something like this. It is the relative distances.
Okay.
And the relative velocities, or the rate of change is then the time derivative of this.
Right, yeah.
And the relative velocities,
The velocity of each.
yes.
Yeah, vector.
So,
Okay. That's
And-
very
subtle difference.
yeah.
yes, but it is extremely important, because this one, if you calculate the inertial masses, then this here gives a tensor. It is a tensorial dependence
The
on,
speed of light.
no, the inertial mass.
Oh, okay.
You get a tensor for the inertial mass. And this is in disagreement with observations, because the inertial mass is shown to be isotropic. That means it is a scalar. And this is also where very many of those papers, like what Schrödinger did and
Prices
what...
as well.
Yes, where they conflicted with the experiment, because anisotropic inertial masses were ruled out very early. And this is also the reason why this has never really gotten the... it was a kind of
Pushed aside, or?
bottleneck for those theories, because everyone said it yields anisotropic masses, and this is in disagreement with observation. But this was because they all tried to do it with the relative distances and their changes.
And that's what Julian says as well, Julian Barber.
Yes, Exactly, and this I had long discussions with him about this until I convinced him that there is a difference between those two. And it's, no, but as you said, it is very subtle. It is really.
I'm trying to think what exactly is the difference, because you take the derivative of the.
If you calculate this, then you get something like this. If you express it in terms of the relative velocities, and this.
What are those brackets?
It is a scalar product.
Okay.
And this is not this. And this scalar product here, this gives rise to the anisotropic inertial masses, because if you take the time derivative of this here, then you get a term which is something like Aij scalar product with R. And that means that the accelerations are direction dependent. If you accelerate parallel to Rij, then you get different accelerations than when you accelerate perpendicular to it.
Acceleration, then these two expressions are the same, right? The R dot and
yes.
Imagine two masses rotating around each other, right? The distance doesn't change, so this Rij dot would be 0.
Yeah, great right? Example. Yeah.
Okay.
But the velocities, the difference between the velocities would not be 0.
Right, but the velocities then depend upon a particular frame of reference, right?
No, this is invariant also, because you have, this is only dependent on relative quantities. So it is also Machian. This, what Assis did is also Machian, because it is also even rotationally invariant. Because
the velocity expression, like, don't you have to have a frame of reference if you're to establish that one of the points has, that each of the points has a particular velocity, and then you take the.
Yes, of course. If you can split this up into the absolute velocities, and this is then, of course, dependent on the frame of reference which you choose. But as long as you let it in terms of relative velocities, then it is independent.
But isn't that not the case because in the rotating frame, right? So in the case that you just pointed out, and where you have like one point which is 0 velocity, and then a particle that's moving like this, but it's rotating around it, then depending on your frame, so if you choose a frame that's not rotating and one that's rotating, then you'll have a different velocity, right?
Yes, of course.
I believe this is.
So it is frame dependent, right? But I mean, I'm not saying this is a criticism, because I think that's how you have to do it as well.
I'm not sure about Assis' theory, because I have not.
Assis' theory won't be frame dependent, because what it'll tell you is whether or not that point is rotating around it, the change in relative distance is going to be 0.
Yes, of course. I think Assis' theory is independent under rotations, because it only depends on the relative distances, and they remain invariant under rotations. Treder's theory, in the form I have just written it, is not independent under rotations. Not yet.
Okay. Although it wasn't. Didn't your gravity-magnetic field that you introduced, doesn't that get you rotation invariance?
No. It is translation. Yes, translation invariance, and the rotation invariance, one has to make a little change to the Lagrange function, but I will. This is the next part.
Okay.
Yeah. Yes. It is just this does not work because it predicts anisotropic inertial masses.
Yeah. Okay.
And this is the reason why you cannot use the rates of changes of the distances.
Yeah.
You have to use the relative velocities to get a scalar dependence from the inertial mass.
Okay.
I will not go into the technical details, just write the expression and show how one can derive it. So now there was, I draw this, the idea from the paper by Lindenberg and Katz. They did it with the first Machian Lagrangian, which I wrote down, which was dependent only on the relative velocities and the products of the masses. And they had a very nice way to make this rotation invariant, and they wrote it as, they expressed the velocity relative to some rotating frame. So then we have, this is the kinetic energy, this term here. And now they minimized this expression with respect to omega. So they demanded that this derivative here vanishes.
Omega is just the total angular momentum of the universe, right?
No, the omega is just an angular frequency. It is, until now, it is just an arbitrary parameter, and we determine it over this equation.
Right.
But this equation here expresses that the total angular momentum of the universe is also zero, because the derivative of the Lagrange function after the angular momentum is after the angular frequency is the angular momentum.
So you could visualize this capital omega as the
angular frequency of the universe
in which you are looking at the universe, right?
Yes, exactly. Yes, it is the angular frequency of the universe perceived in the frame where you write the equations. Yes. And we had, at the beginning, we saw that the momentum of the universe, the total momentum of the universe is zero, and this equation here states that the angular momentum of the universe is also zero. Yes, from this one gets an equation for this omega, and one can write this in the I equals I times omega, and J is given by something like this is so to say the definition for the omega, which one gets from this. So we demand this. This is the idea of Lindenbell and Katz, and then we get a relation between J, I, and omega, and this is so to say the definition for the omega, because these two quantities are calculated by just the mass distribution of the universe and their velocities. This is something like a moment of inertia tensor, and this is something like the angular momentum of the single particles, but again just depending on the relative quantities, and this defines our omega. So this is something like the angular frequency of the universe, and it is something like, if we formally invert this matrix, we get something like this for the angular frequency of the universe. This expression is rotationally invariant. It is independent of the frame chosen to write it in. And yes, one can now also derive equations of motion from this Lagrangian. This is very technical, or it's a bit technical to do this. And one gets, yes, very similar expressions to the one we already got, just yes, in a rotating frame of reference, and it is the frame rotating with this frequency omega of the. I will not write down the equations in detail. I will not write down the second term. It is just the Gravo-electromagnetic force, which we derived in the first part, as perceived in the rotating frame, which is rotating with the frequency omega. But what is more interesting is this term here. It is just the expression for the fictitious forces. We have an Euler force, a Coriolis force, and a centrifugal force, which depends on the angular frequency of the universe. So whenever we are in a frame rotating relative to the universe, then we get a fictitious force, the Newtonian fictitious force, which is proportional to the angular frequency of the universe. So, and this is yes, resolves what Mach was criticizing in Newton's bucket experiment, because he said that one would not know what would happen when the universe were rotating but the bucket was stationary. And the answer in Treder's theory is that indeed, if the universe were rotating with a frequency omega and the bucket was stationary, then the water in the bucket would actually experience exactly the same fictitious force than it would experience if the water itself were rotating or the bucket were rotating and the universe was stationary.
So you have got rotational invariance from the original Lagrangian.
Yes, this is the step from here to here. This is not rotation invariant, but this is.
But you can justify that step. Isn't it already part of the beta ij? Right? Because you would get the velocities of all the particles would produce the Coriolis field, right? In the beta ij term.
Not in the first one. If you try it with this one, you don't get this fictitious forces.
So remind me, those are like the relative velocities.
This depends on the relative velocities to the rotating or to the rotation of the universe, and this is just dependent on the, so to say, from a rotation perspective, these are absolute velocities.
Could it be that there's a kind of fault you mentioned earlier, that the beta is defined by the very fact that it doesn't include vectors, but just is considering just the relative distances as
exactly.
Could that be the problem?
Could you get around that issue exactly by choosing a frame-dependent term rather than a totally internal term, and then just contain the omega inside of the.
Yes, I mean you can define this here as something like beta ij dash or something like that, and this is then independent of the frame you choose to write it in.
Or rather, it's frame dependent because you want it to co-vary on the frame transformations, on the rotations of the frame, right?
But this remains invariant. This is frame dependent, and this is. But if you rotate the frame, then both contributions you get from the transformation from this term and from this term cancel each other out. So this here is independent. And you want the law, the Lagrange function, to be valid in arbitrary rotating frames.
Okay, that's confusing me a bit, because then how do you get the force law if those two cancel out?
I believe I agree with Jonathan. You don't actually want the Lagrangian to be independent under rotations, because when you apply the Euler-Lagrange equations, there somehow the angular orientation of the frame is baked into them, right?
No, but that really is the mistake or the problem in the common theories, because you get you only get the inertial forces on one side, but you really want to have them on both sides, so that your equations stay invariant under transformations.
But you want your Lagrangian to be covariant, right? To change on reference frame transformations, because the Lagrangian gives you your forces, and you want your inertial forces to be covariant on the reference frame transformation, so that whichever frame you choose, that you'll get the appropriate inertial forces.
Yes,
right?
of course.
And so, but that means we should have a Lagrangian that isn't frame invariant, but rather depends on the frame.
No.
This was Sciama's approach.
The problem in Newtonian physics is that you get the inertial forces only on one side.
What do you mean on one side?
You have, on the one side you have the accelerations, and on the other side you have the force. And if you transform into any frame, then only the velocity or the accelerations change. You get the inertial accelerations from the transformation of the velocities, but the force does not change. But you really want...
That just depends on your definition, because you can introduce an inertial force field and then your force
Yes,
field.
but this is the point. You have to introduce this force field. You have to postulate that inertial forces are additionally present in a rotating or in an accelerating frame. And this is exactly what Treder's theory tries to explain, that you do not have to postulate these forces when you go into an accelerated frame, but they come out of the gravitational field. So the gravitational field produces, when you transform, the same forces that you on the other side get from the velocities.
Okay.
I believe
I believe you both are right, but
I think we're maybe talking past each other.
This can be yes.
yes. So what Jonathan says sounds more logical to me too. That the Lagrangian would somehow have to co-vary under arbitrary transformations, but maybe it's a matter of viewpoint. Have to think about it.
Yeah,
Because if the Lagrangian was invariant on the transformations, then you wouldn't be able to derive the inertial forces from it, because you would have the same force, whatever.
No, it can't. You don't, because you. It depends on where you express the. In which frame you express the velocities.
Yes, but that's the point. Is that the Lagrangian then depends on the frame that you express the velocities in, right?
The force equations that you get depend on the frame where you express the velocities in.
Yeah, but they come from the Lagrangian.
Yeah, but maybe there is indeed a danger that someone's talking past each other. I don't know. I really can't. I'm kind of lost a little bit. Ask you excuse if I divert a little bit now. What I remember, you said you took inspiration from Lindenbell and Katz, and I kind of faintly remember that it was very intriguing, but he missed somehow the point to explain the gravitational constant. Can you explain where exactly, this Treder's approach diverges from, or how it distinguishes it?
The 1/r term here. Lynden-Bell only took this.
Okay, I see. Yeah, I see.
Because he actually did the same what was done here with the angular frequency. He did with the Newtonian kinetic energy and expressed it relative to some frame moving with a velocity v, and then he minimized with respect to this parameter and found that v is something like the center of mass velocity of the universe. And then you can plug this back into the equations, and then you get the same as here, but with the 2 times the total mass of the universe standing here. And then you don't have both terms being proportional to the gravitational potential, and you can't cross the gravitational constant out. It remains in the equations. This only works if both terms, the kinetic and the potential, are proportional to the gravitational potential, MIMJ over RIJ. So this is the difference to what Lynden-Bell and Katz did.
Can I comment again on your disagreement? I believe I have an idea how to work it out. So this is the Lagrangian of the entire universe, right? And if we shift the frame of reference, we change the frame of reference, the beta vector would change and the Rij vector would change. But the entire Lagrangian would stay the same, right?
Yes.
But if you now shift your viewpoint away from the entire universe and try to extract the Lagrangian of a single particle inside the universe, this Lagrangian would not stay the same in this.
Yes, exactly. Exactly, this is the point.
It's the Lagrangian for a single particle that gives you the equations of motion for that particle. Is that right?
Yes, that.
Okay, so that's.
But it's also in the entire Lagrangian because you can just. So this Lagrangian is dependent on lots of variables, and you can just take the Euler-Lagrange equations for a single particle out of it.
Okay, I see.
Can I wipe this out? Because I can actually demonstrate a calculation for the linear case. In the rotational case, it works exactly. We can also shift this to later.
Yeah, maybe it's not a bad idea. If you don't mind, I have you can wipe it out. But I have a more general remark again. We're trying to remove the gravitational constant and to explain it with other things. So I frequently consider physical dimensions, and we have meters and seconds and kilograms, which are somehow related to the three constants h, c, and g by Planck. Do the definition explicitly, and then you have, once we remove the gravitational constant, so there should be a possibility also get formally rid of the unit kilograms. And I think you were quite close to that step, but maybe we can try to make that explicit in a way to kind of clean up the field, to make things more transparent and visible. Do you see, or any of you, a possibility that we recently might get rid of?
I think it's already.
Or is it already done and I overlooked
because
it?
If you scale your kilograms by some arbitrary parameter, so every mass doubles, then you'll get the corresponding change in the gravitational constant that will make sure that things stay the same, I think.
Yeah, that's true. But still, I believe, so yes, of course, physics would stay the same if you just scale up masses and there are just relations of masses to each other and no absolute masses in here. But still, you cannot entirely get rid of the unit of kilograms at this point, I believe, because these theories make no assumptions about the microscopic nature of mass.
Yes.
And you would somehow have to understand how
Exactly.
how the masses interact
Yes.
on a microscopic level to produce these effects.
You still have the gravitational masses. You only really got rid of the inertial mass, but the gravitational mass still is there. And you, as you said, you would have to find a theory of matter which explains what mass is, I think, to remove the kilogram.
Don't we think of it in terms of energy, right?
Yes, then you could do it, yes.
But the unit of kilograms is still in the energy. Unit of energy, right?
Yes, but I think it's not so much a problem because you have to introduce a unit just in order to compare. You just introduce a unit so you can compare one value to another, and we have to have like ratios of masses, so we have to be able to compare them to each other. But as long as the physics is invariant under changes of units, so like kilograms to changing to different, like doubling all of your values, as long as the physics is invariant, then it should be fine. And you don't have this kind of like absolute reference anymore.